Hello. In this video, we will go through experiment number 9 of EP, which is emitter follower as a buffer. So emitter follower is nothing but a common collector transistor configuration. So today we will see this common collector configuration, but before starting the discussion, let us compare this CC configuration with the CE configuration circuit wise. So we have already learned the CE configuration in experiment number 7. So this is nothing but the CE amplifier circuit. So let us learn how this CE amplifier and CC amplifier are different circuit wise. So very first thing, here you can see that this is RC, collector resistor is there. So collector resistor is removed in common collector configuration. So here you can see that there isn't any RC. So collector terminal is directly connected to VCC. That is the very first difference. Now here in common emitter, you can see that the output voltage is taken from collector terminal. So in common collector configuration, instead of output from collector terminal, it is taken from the emitter terminal. So here you can see that output is taken from the emitter terminal. Now here you can see that this capacitor C2, which works as a bypass capacitor in common emitter configuration, now this C2 becomes coupling capacitor. You can see that this C2 becomes coupling capacitor. Now in CE configuration, due to this bypass capacitor, this RE will become short circuit in AC analysis, and so that this emitter terminal will be grounded. Now similarly, in case of AC analysis of this CC configuration, we can say that this collector terminal will be at the AC ground, because in AC analysis this BC battery will be grounded. So we can see that this collector terminal will be directly grounded. Now in that sense, we are applying input between base and ground, and since collector is ground, so we can say that we are applying input between base and collector, and we are taking the output from emitter and ground, and since collector is at AC ground, so we can say that we are taking output from emitter and collector. So here collector is common in between input and output. So in that sense, this configuration is called common collector configuration. Now if you go through the theory of this common collector configuration, then AC voltage gain theoretical will be AV is equals RE upon RE dash plus RE, where this RE is nothing but RE parallel RL. So here you can see that this small RE is nothing but this emitter resistor in parallel with the RL. So parallel combination of this RE RL becomes small RE, and RE dash is nothing but the AC emitter resistance. Now here we know that RE will be in terms of kilo ohm and RE dash will be few ohms. So here you can see that this RE dash will be very much small compared to this small RE. But due to presence of this RE dash, we can say that though it is small, but due to its presence, this numerator, okay, compared to this numerator, this denominator term will be slightly higher. This denominator is slightly higher. So we can say that the ratio of this numerator by denominator will be less than 1. And here, since this RE dash, which is few ohms, and it is too much less than this RE, which is parallel combination of RE and RL, so it is very much less. RE dash is very much less, so one can neglect this RE dash. So if one neglect this RE dash, then the ratio is simply RE upon RE, which is 1. So here one can say that the voltage gain, AC voltage gain of this CC configuration is nearly 1. Now, if we talk about the DC current gain, so here DC current gain is nothing but the output current upon input current. So since input is nothing but your base current IB and output we are taking from the emitter terminal. So IE is the output current. So here the IE upon IB is nothing but the DC current gain. We know that IE is nothing but IC plus IB. So if you simplify this equation, so this becomes IC upon IB plus IB upon IB. And we know that IC by IB, which is nothing but the beta DC, and this IB by IB becomes 1. So this equation transforms into beta DC plus 1, and beta DC is too much higher than the 1. So this answer will be approximately equal to beta DC. So in this sense, you can say that the DC current gain of this CC configuration is approximately beta DC. So here you can see that this CC configuration, yes, this CC configuration provides AC voltage gain nearly equal to 1, but yes, it provides DC current gain, and that DC current gain will be equal to beta DC. So here you can say that, let us assume that input voltage signal applied is nothing but a 2 volt peak to peak sinusoidal wave. So output voltage in this case will be approximately equal to the same 2 volt peak to peak sinusoidal wave. So here we can see that we know that AC voltage gain practical is nothing but output voltage peak to peak divided by input voltage peak to peak, and in this CC configuration output voltage will be same as the input voltage. So here if you put these values 2 volt by 2 volt, so you will get that AV will be equal to 1. But practically output voltage is slightly lesser than the input voltage, so practically we will get AV which is slightly less than 1. So here we can see that AV, but in general terms voltage gain will be nearer to 1, because if 1 is approximating 0.9 with 1, so in that sense we can say that the voltage gain will be approximately 1 in this CC configuration. Now another thing is what, since output voltage is same as the input voltage, yes, you can see that output voltage is 2 volt peak to peak sinusoidal wave, which is same as input voltage, which is 2 volt peak to peak. And yes, and we are taking the output from the emitter terminal, so we can say that the output available at the emitter terminal is following or copying the input voltage. So in that sense, another name of this circuit is nothing but emitter follower. Yes, emitter follower, because output voltage is following the input voltage. So in that sense it is follower, and since output is taken from emitter terminal, so this is emitter follower. This is one another name of this CC configuration. Now here we can say that since output voltage is same as the input voltage, so here you can see that output is same as input voltage, so we can say that input is not processed, or input voltage is not processed, it is passed as it is. So another name is voltage buffer. Yes, another name is nothing but the voltage buffer. Now here, since voltage is passed as it is not processed, and we know that in buffer circuit the in buffer circuit output will be same as input. There is no change in the output compared to input, means we can call it as one kind of delay. So since output voltage is same as input voltage in this CC configuration, so another name is nothing but the voltage buffer, or simply buffer. Actually it is voltage buffer. So let us move ahead. Now here the circuit given in the manual is this one, and circuit which we will implement is nothing but the described over here. So we will implement this circuit in a multi-sim simulator and we will take the readings. Now if we go through the procedure, that very first step is nothing but the make the required connection as shown in the figure. So I have prepared that circuit already in the multisim, and that circuit will look like this one. Here you can see that this is the circuit. Now here another step is select the R1, R2 10K, RE 1K, RL 2.2K. So here I have set the same R1, R2, RE, RL, and I have also selected the C1, C2 1 microfarad. So C1 and C2 are 1 microfarad. So the same circuit I have connected. Now next what we have to do is we have to check the output voltage on the CRO and measure the gain. So here you can see that input is applied and we have to check the output at the load resistance RL, and we have to measure the gain. So next step is once you measure the gain, then you have to repeat the experiment with different input signals and note down the output observations in table 9.1. So here you have to repeat the whole process and you have to apply the different input signal, vary the input, take the output, and once again calculate the gain. For different input, find out what is the output and calculate the gain. And we have to note it down into table number 9.1. So here we can see that this is table number 9.1, which says that the variation of gain with respect to V in. So here it is nothing but the V in, input we will vary, we will measure this V out, then we will calculate gain observed practically. So practical gain is nothing but we know that what is the output peak to peak divided by input peak to peak, and gain theoretically, yes, gain theoretically, that you have to calculate using equations. Now equations of calculating the theoretical gain is provided in the manual itself, and it is also available in the book. So you have to put this all values and find out the voltage gain theoretical. So let us move to this table number 9.1 and let us simulate the circuit and get our results. So let us start with varying the input voltage. So here one table is prepared where we will take this much different input voltage and we will find out the output voltage, corresponding output voltage we will find it out. And once we find out the output voltage, then you have to calculate gain observed and theoretically and practically, both gains you have to calculate over here. So let us start with the first input, which is nothing but the 40 millivolt peak to peak to the input of CC amplifier. And yes, here we will take the VCC equals 10 volt, which is fixed. So let us move to the circuit and let us apply the 40 millivolt peak to peak. So let us move to the multi-sim and take the output. So here you can see that this one is nothing but a circuit, and we will vary the input voltage over here and take the output voltage across load resistance RL. Now here input is connected via blue line and output is taken from this red line. So blue one will is your input and red one is nothing but the output. And our first input is nothing but this 40 millivolt. Yes, 40 millivolt peak to peak. So that's why it is already set to 20 millivolt peak. So 40 millivolt peak to peak is fine. So now let us run the circuit and observe the output voltage. So if I press the run button, okay, so simulation is started, and now let us observe the oscilloscope screen. So let us move to that oscilloscope. So here you can see that how it looks like. So this one is oscilloscope, and let me set it. This blue one is nothing but your input, and red one is nothing but your output. So let me set it properly. So red one is nothing but output. So here you can see that once I set the scale of both channels as 10 millivolt per division, 10 millivolt per division, you can see that there isn't any major difference between the input signal and output. So input is blue one, output is red one, and they are overlapping. So in that sense, you can see that output is same as input. Output is following the input. But here we are interested to measure the peak to peak of the output voltage. So let me temporarily make this input signal off. Only red one will be available, and let us measure the peak to peak of this output signal for the input 40 millivolt peak to peak. So let us measure it. So here if I pause it, and if we try to find out the peak to peak, so if I set this cursors, and here look, you have to observe over here, this value must be maximized. You have to put your two cursors such a way that, okay, one at the top and another at the bottom of this sine wave, so that you get the difference maximum, and that is your maximum possible output, that is peak to peak. So here we are getting, okay, output voltage is 39.263 millivolt. So 39.263 millivolt, 39.263 millivolt. Obviously it is peak to peak, it is peak to peak. So when input is 40 millivolt, your output is 39.263 millivolt. So you just note it down. Now let us change the value of our input peak to peak. So next one is nothing but 500 millivolt. Yes, peak to peak is 500 millivolt. So let me pause this and change this value. So 500 millivolt peak to peak. So I can say that 250 millivolt peak. So 250 millivolt peak, that is 500 millivolt peak to peak. And let us rerun it. So if we rerun it, yes, and once again let us try to observe the CRO. So let me change that. So if we try to observe this oscilloscope, so here you can see that red one is your output, and if I set the scale properly, yes, you can see that this is your output signal. Let us measure peak to peak for input 500 millivolt. So if we set the cursors, okay, one at the top, one at the bottom, and if we try to get the answers, so these are nothing but 492.273 millivolt. Yes, 492.273. So 492.273 millivolt. Yes, that is our answer. Now let us move to the next input, which is I think 1 volt peak to peak. So let us move to our that circuit. Yes, and change it to 1 volt peak to peak. Yes, third one, 1 volt peak to peak. So 1 volt peak to peak. So I have to set my source to 0.5 volt peak. 0.5 volt peak. So here you can see that it is changed to 0.5 volt peak, which is 1 volt peak to peak. And let us run it once again. and try to observe the CRO. So what we will get in the output, so here you can see that the output corresponding to 1 volt peak to peak input. Now if I try to pause it, yes, and measure peak to peak, so one at the top, okay, set second cursor at the bottom, and here I am getting the, let me set it to make to get the maximum answer. It is 985. Yes, this is the, I think, maximum 984 point something, or yes, 984.482. Write down 984.482. 984.482 millivolt. Yes, peak to peak. So this much output we are getting when input is 1 volt peak to peak. So let us move to our fourth reading. So let us change the input once again. So here let us move to the last reading, which is nothing but 2 volt. Yes, 2 volt peak to peak. So if I adjust it, so 2 volt peak to peak is nothing but 1 volt peak. So let us change it to 1 volt peak. So here you can see that now your source is giving 2 volt peak to peak. Frequency is same, yes. For all readings, we are having the same frequency 1 kilohertz. We are changing only peak value. So here, let us observe, let us run it and observe the output of the oscilloscope. So here, let us move to this oscilloscope and get the output voltage. So here you can see that this is oscilloscope, and let me set the proper voltages and pause it. So if I pause it and put the cursor one at the top of the sign and one at the bottom of the sign, yes, you can see that this is, yes, 1.970 volt. Yes, 1.970 volt. So please note it down. Output is 1.970 volt, while input is 2 volt. Yes, 2 volt peak to peak, while input is 2 volt peak to peak. So here you get the output voltage for the fourth reading. So hope you understand it and get it, how we are changing the input and we are getting the output peak to peak. Yes, so here I can see that all the readings for different inputs, we have noted it down. So let us move to that observation table. Yes, let us move to that observation table. So here we can see that, okay, so here is nothing but our observation table. So for 40 millivolt, we are getting 39 point something. For 500 millivolt peak to peak, we are getting 492 point something. 1, it is 0.9 something, and 2, it is 1.97. So now you have to calculate this gain observed practically, which is nothing but output voltage peak to peak over input voltage. So if you take the ratio of V out upon V in, so obviously you will get some 0.9 something, and that ratio will be always less than 1 or nearly equal to 1. You can approximate to 1. And next you have to calculate the gain theoretically. Yes, you have to calculate gain theoretically, whose equation are provided in the manual itself. So let us move ahead. Next one is, yes, next says what? Now fix the value of input AC signal about 20 millivolt at 1 kilohertz frequency. Yes, so we will set our input at 20 millivolt peak at 1 kilohertz frequency and measure the output voltage at different values of VCC. Okay, and note down the theoretically calculated and practical gain. Yes, same thing, but now what we have to do is we have to fix the input AC signal. input AC signal we will fix it, and we will measure the output voltage. Yes, output voltage for the different value of VCC. So we will change the VCC over here. So let us move to table number 9.2. So table number 9.2 says what here. So here you have to set the input voltage 1 volt peak to peak, and frequency is 1 kilohertz. That you keep it fixed and vary the VCC. So various values of VCC we have to vary. We have to note down the VO. We have to calculate this practical and theoretical gain. So let us go for it. But before this, what will be the effect of increasing VCC in our circuit? So let us try to understand it. So if we move to the theoretical equations, so here you can see that if we increase the VCC, so obviously VCC increases, so you can say that VBB increases. Now if VBB increases, then VE is nothing but VBB minus 0.7. So if VBB increases, so your VE increase. If VE increase, IE, ammeter current increases. Now, if ammeter current increases, then you can see that the ammeter dynamic resistance RE dash will also increase. And if RE dash increases, then we can say that IE increases, RE dash decreases. Yes, IE, because ammeter current is increasing, RE dash is decreasing. And if RE dash decreasing, you can see that, look, this term, RE dash is decreasing. So we can say that since the denominator is decreasing, your practical gain will increase. Yes. So conclusion is what? As VCC increases, yes, your gain will more tends to 1. If it is, for example, if it is at 0.91, so if it will move to 0.94, 0.95, 0.96 as you keep on increasing the VCC. So that effect we have to measure. So let us go for it. So here we will go with input voltage 1 volt peak to peak, keep the 1 kilohertz sine wave input, fix and vary the VCC for 3 different voltages. So let us move to the circuit, but during that you just prepare this table. Please note down this table in your notebook, and now we will vary the VCC. Okay, so let us move to the circuit. So this one is nothing but circuit. Now here let us first fix the input. Yes, because we are asked to fix the input, which is 1 volt peak to peak. So I have to set the 0.5 as a peak. So if 0.5 volt is a peak, so your input is at 1 volt peak to peak and frequency is 1 kilohertz. Yes, and right now VCC is set already 10. Yes, look, first reading is nothing but the VCC 10 volt. So VCC is already set to 10. So let us run it and measure the peak to peak. So if I run it and open the oscilloscope, so let us measure the output peak to peak. So here you can see that this one is nothing but the peak to peak output. Let me pause this so that we can measure this peak to peak. So if I set one cursor on the top of the sign, another to the bottom of the sign, yes, you can see that this is nothing but 984.482 millivolt. 984.482 millivolt. Yes, let me write down 984.482 millivolt. Yes, this is the output corresponding to input 1 volt peak to peak. Okay, so let us move into the next one, which is nothing but next value of VCC, which is 15 volt. Yes, 15 volt. So now let us change it to 15 volt, and once again we will measure the peak to peak output. So here it is 15 volt. Yes, you can see that instead of 10, VCC is now 15 volt, which is our second reading. So let me rerun it, and let us move to the oscilloscope So here you can see that we are getting the output, but let us measure it properly. If I pause it and try to get the value by putting the cursor, so you can see that yes, we are getting 988.106. Yes, 988.106 millivolt. Yes, 988.106 millivolt. That is our output. Okay, because look, we are keeping the input voltage peak to peak fix. We are changing only the VCC. We are not changing the peak to peak of the input. Peak to peak is still 1 volt peak to peak. So here is the second reading. Let us move to the next one and last one, which is nothing but VCC equal 20 volt. So if VCC is 20 volt, so let me change it to 20 volt. So instead of 50, let us move to the last one. Yes, 20 volt, and rerun it. And let us move to the oscilloscope. So if we move to the oscilloscope and try to measure the peak to peak of the output once again, then here you can see that if I pause it and put the cursor at the proper value, that is one at the top of the sign, another at the bottom of the sign. So here you can see that this is it maximum? Yes, 990.409. Yes, 990. Please write down. It is 990.409 millivolt. Fine. Yes. So this one is our last reading. So let us move back to our circuit. Yes. So here we have changed the values of VCC. Yes, here we have changed the values of VCC for the fixed value of input. Look, we have not touched anywhere over here. Input is fixed. We have only varied the VCC. So now let us move to the table number 9.2, that is the readings. So if we go through it, then yes, this is our table, and this table says here, this table says as we increase the VCC 10, 15, 20, and you can see that there is a slight increase in the output. Yes, because we know that we have already discussed that because on increasing the VCC, your ammeter current IE increases, so I dash decreases, and I dash decreases. What does it mean? Your AV gain tends to 1. So here you can see that if you take the ratio of V out upon V in is nothing but 1 volt. Yes, you can see that V in is nothing but the 1 volt. So you can see that your observed gain, which is output, this output divided by the 1. Okay, so that will be higher, that will move to the 1 as we are increasing the VCC, and at last you have to calculate the theoretical gain. So now your job is to find out this practical gain column and theoretical gain column for both table 9.1 and table 9.2. So let us move ahead, and these are the readings that you can note it down. Let us move ahead. Now finally you have to write your own conclusion. Yes, this is the end of the experiment, and now you have to write down your own conclusion properly, that what you understood from this experiment. And let us move to the last topic that we learn today, or go through the experiment of ammeter follower as a buffer, and this is nothing but voltage buffer. Okay, because why? Because you get the same output voltage as the input voltage. There is no change in the voltage, output voltage waveform. Okay, it is same, but yes, there is change in the current. Yes, this will provide the current gain. So ammeter follower is nothing but the common collector amplifier, and is nothing but the voltage buffer. Now another interesting thing is nothing but in a book you will find out that input impedance of this CC amplifier is higher compared to the output impedance. Yes, so input impedance is higher and output impedance is lower of a CC amplifier. So let us take one case that common emitter amplifier is connected to the low resistive load. Yes, that is output of the common emitter is connected to low value of resistive load. So what happens, since the resistive load is having low value, so obviously it will draw more current from the common emitter amplifier circuit. Yes, because emitter amplifier, this is C amplifier, is a source, so load will require more current from the source, and this situation is called the loading effect. Yes, it will overload the source because it needs a more current. So this is called loading effect. And to avoid this kind of situation of the loading effect, what is the solution is insert this CC amplifier stage between this source and load. So if we insert the CC amplifier this stage between this source and load, here we can see that now what happens, since load requires higher current. Yes, since load requires higher current, so here we can see that the CC amplifier, what it does, it is nothing but kind of a current amplifier. So here we can see that CC amplifier will take less current from the common emitter amplifier circuit. It will take the less current, it will multiply that current with beta DC times, and it will provide the higher current to the resistive load, low value resistive load. So here you can see that the requirement of the current of the low resistive load is fulfilled. So now your CE amplifier is not overloaded. Yes, CE amplifier is not overloaded due to insertion of this CC amplifier. Now this CC amplifier, we can say that since voltage gain is 1, so whatever the voltage signal as an input, same voltage signal will be output, but you can see that the current capability of this whole stage is increasing because of insertion of this CC amplifier. Now another interesting thing is what it also does, impedance matching. Now impedance matching means the load is having low resistance, and compared to load this CE amplifier is higher resistance or higher impedance. So we can say that initially when this stage was not present, so there was connection of low impedance load and high impedance source which is not matching. But now due to insertion of this CC amplifier which is having high impedance, input impedance, and low output impedance, what happens, the high output impedance of CE amplifier matches with the high input impedance of the CC amplifier, and low output impedance of the CC amplifier matches with the low impedance load resistance. So in that sense we can say that now there will be no loading effect on the source, and this CC amplifier also performs the function of impedance matching. It is also same time working as a voltage buffer, and it is also increasing the current driving capability of the source so that source become no more overloaded. So in this way CC amplifier is very useful in increasing current capability and also impedance matching. So you can call it as a CE-CC cascaded stage, and with the help of this CE-CC cascaded stage you can drive the load resistance which is having low value of resistance. So you can drive the low resistive load with the help of this CE and CC cascaded configuration. So in the assignment questions you are asked to draw the cascading connections of CE and CC amplifier, so that you can find out in the CC and CB amplifier chapter of the book by Albert Malvino. And yes, you get some overview of the cascaded connection of CE and CC amplifier. Another question is about common base transistor amplifier shown in figure, and you have to calculate theoretical gain, So theoretical gain equations are provided in the same chapter of CC and CB amplifier. You can find out and calculate the gain. About practical application in electronics, so CB configuration like CC configuration, here you can see that in CC configuration, high input impedance, low output impedance, exact opposite occurs in case of CB configuration. So CB is having low input impedance and high output impedance. So the situation where source is having low output impedance and load is having the high input impedance. So in that case, if you want to match the source with high impedance and load with low impedance, so in that case CB amplifier will be used. So CB is also useful in impedance matching, but in a particular case. So you can complete these assignment questions on your own now. So this is the end of this session. Thank you.